Hi everyone, welcome to my talk. I'm Weena from Carnegie Mellon University. Today I'd like to talk to you about our work on zero queuing for multi-server jobs. So this is joint work with Qiangmin from Cornell University and more from CMU. So let's get started. First thing first, what is a multi-server job? To better understand this, let's start with a single server job. So this is the traditional job model. When we schedule a single server job, we put it onto one server and it gets completed there. A multi-server job, on the other hand, requires multiple servers. So for example, this green job, it requires 4 servers, and we see that it has a server need of 4. And then when we put it into service, we need to allocate 4 servers at the same time to this job. So this is like a family of 4 going to a restaurant, and the servers are the seats in the restaurant, and we can only serve this family if we can seat all of them. So when we think about the scheduling problem for data centers, then over the years we have witnessed a rapid growth in the sizes of data centers, and the server needs actually grow together as the data centers grow. So this is a figure generated from trees from Google, and the x-axis is the server need, and the y-axis is the corresponding fraction of jobs. And as we can see here, the server needs ranges from 1 to all the way to more than 10 to the 5, so it can be very large. So motivated by this new emerging paradigm in computing clusters, we're going to study multi-server jobs in the following model. So in this model, we have n servers, and the jobs come into a central queue. And the number of circles in each job indicates its server need. So for this red job, it is currently in service, and this server need is 5. So it occupies 5 servers at the same time. And we classify jobs into K-job classes based on their server needs. For class I jobs, the arrival is a Poisson process with the rate lambda I, and the server need is Mi. And when it goes onto the servers, it holds Mi servers for exponential mu I time. And so this is a summary of the parameters for class I jobs. When we schedule jobs, we schedule them from the queue in a first come first serve manner. And this is the default policy being used by Google right now. So we examine the number of available servers and see if we can schedule the next job in the queue. So in this example here, we have 2 idle servers, but the job at the head of the queue is the green job, which requires 4 servers. So we cannot accommodate this green job, and those 2 servers need to remain idle. And this wastage here is not just not specific to the first come first serve policy, but it's intrinsic due to the fact that a job now can occupy multiple servers at the same time. And actually the results I'm going to present generalize beyond first come first serve policy. So there's another interesting phenomenon that cannot happen for single server jobs, but it can happen to multi-server job systems. So for example, if we look at this red job in service, when it departs, it frees 5 servers, frees up 5 servers. So we have 7 available servers in total. That is enough to accommodate the next 3 jobs in the queue. So these 3 jobs are going to enter service at the same time. On the other hand, if the blue job departs, then the number of available servers is 3. That is still not enough to serve the green job here. So then in this case, no jobs in the queue enter service when the blue job departs. So there's a jitter effect here, and it makes the queuing dynamics quite complicated to analyze. So for a multi-server job system, we need to re-examine the notion of load. Traditionally, it's defined through this ratio between arrival rate lambda I and the service rate mu I. And 1 over mu I here captures the time we need to finish a job. But now if we have multi-server jobs, then this definition of load no longer captures the fraction of busy servers in steady state. So we need to fix that by adding the server need Mi to the numerator. And this ratio now between Mi and mu I is the product of the server need and the time need of a job. So this is consistent with the notion of CPU hours used in practical systems. So with this model, we want to understand the latency of jobs, especially the time a job spends waiting in the queue. So in this talk, we are going to focus on the probability of queuing, also called the queuing probability. And it is really desirable to have a very low queuing probability because that means most of the jobs can enter service directly without queuing. So this problem, this model has been studied in the literature, but little progress has been made in terms of understanding latency of jobs. So the exact solutions of steady state distributions are only known when we have a system with two servers. And in fact, even characterizing the exact stability region is hard. It is only known when all the job classes have the same service rate or when we only have two job classes. So our multi-server job model is also related to the loss model in the system and also virtual machine scheduling problem. So in summary, characterizing latency of multi-server jobs has been a hard problem. So how can we make progress on this front? What new perspectives can we provide? So if we look at a modern computing cluster, one of the most notable features is that it has a large number of servers, as we mentioned at the beginning of the talk. So the number of servers in is really large here. So this complicates the analysis because the state space is enormous due to the large N, but actually it also brings a new perspective to the problem. So can we actually analyze the queuing probability in scaling regimes when N goes to infinity? And then the limiting behavior of the queuing probability provides a very good approximation to the original system because N is very large. So actually, we do understand the queuing probability in some settings in the scaling regimes. So for example, when we have only one job class and the server need is 2, then this is effectively a MM n over 2Q. And the classical results in the literature provide this table to us. So here, rho is the load of the system, and we use the superscript n to indicate that the load depends on n. And then depending on how the load scales with n, the queuing probability can converge to 0, to 1, or something in between. So in particular, we are interested in the case when the queuing probability goes to 0, because that means most of the jobs go into service directly without queuing. They don't have to wait at all. So this is what we want, and this is what we mean when we say zero queuing. So this table here provides very insightful understanding for the provisioning needed to achieve zero queuing. However, as we mentioned at the beginning of the talk, the server needs also grow when n grow. So the server needs are also large. Then instead of having jobs with the server need equal to 2, we may have jobs with the server need that is really large as half of the servers. Then in this case, are those existing results still true? So when we look at this system, if the server need is n over 2, then this is effectively a MM2Q. And for MM2Q, because the number of servers is 2, is a fixed number that doesn't depend on n, those scaling results are no longer true. For example, for the scaling regime in the first row, when the load is on the lighter side, the queuing probability no longer converges to 0 due to the fixed number of servers here, which is 2. And more generally, we have different job classes with the different server needs. And in this case, the load is also defined, like recall that the load is defined in this following way, which is different from the traditional notion. So here we have a rev rate lambda I and a server need mi, and we put the superscripts to both of them because they can both depend on n. And as we just saw, if we only know how the load scales within, that's not enough to tell us how the queuing probability is going to behave. So we also need to know the server needs. Therefore, we propose new scaling regimes that take into account both the scaling of the load and the scaling of server needs. So under those new scaling regimes, can we analyze the queuing probability? So more specifically, we have a joint scaling regime where both the load scales with n and the server needs scale with n. And we want to understand the queuing probability on this joint scaling plane. We want to identify regions for the queuing probability to go to 0. So our answers are as follows. So when we scale the load, we scale it in the following form, which is in this form with the parameters alpha and beta, so they are constant. And alpha is the key constant here. The larger alpha is, the faster the load approaches 1. And that means the traffic is heavier. So we put alpha on the x-axis. So now let's scale the server needs. Let's focus on the maximum server need among all the job classes and assume that it scales in this form. And the gamma here is the key parameter. And the larger gamma is, the larger the server needs are. So we put gamma on the y-axis. So as a warm-up, let's look at the x-axis. And this is the case where the load scales with n, but the server needs doesn't scale. And for we can show that if alpha is not super large, if alpha is strictly smaller than half, then the queuing probability goes to 0. So this recovers the classical results for queuing probabilities in the scaling regimes called the sub-halving weight regime. Now let's look at the y-axis. This is the case where the server needs scale, but the load doesn't scale. And we can show that when gamma is strictly smaller than 1, again, the queuing probability goes to 0. So now let's move on to this plane where we have a truly joint scaling between the load and the server needs. And we identify that the region below this line here gives 0 queuing, achieves 0 queuing. And so intuitively, if we want the queuing probability to be small, then it cannot be the case where both alpha and gamma are large. So they have to be constrained. And our results give a condition with explicit condition that guarantees 0 queuing. And this condition happens to be a linear relation among between alpha and gamma. So the condition is tight in the sense that for all the points outside the green region, the queuing probability doesn't converge to 0 when we have a single job class in the system. So in fact, our results are more general than what's being visualized here. So we actually prove a theorem that establishes an upper bound for the queuing probability in terms of the load, the maximum server need, the system size n, and the number of job classes k. So let's understand this expression a little bit better. So first, among the two terms in the parentheses, the first one is the dominant term. This is because we make an assumption that the maximum server need is much smaller than n. Then to make the queuing probability converge to 0, a sufficient condition is this, which is the denominator here is much larger than the dominant term. And then we can write this in the equivalent form by just moving the terms around, and it has this form. And this form here allows us to explain this condition. So let's start with the term on the left, and let's focus on all the jobs with the maximum server needs. And then n divided by m max is the total, the maximum number of such jobs that can go into service, onto the servers at the same time. So this ratio is the effective number of servers relative to the maximum server need. Now let's look at the right-hand side. The first term is n divided by m max timed by the load. Since the load reflects the fraction of busy servers, this is the average effective number of busy servers. And then this square root term, this is the square root term of the mean, and it actually is roughly the standard deviation for the effective number of basis servers. So this condition actually says that the total effective number of servers is much larger than the average effective number of basis servers plus its standard deviation. So that means we almost always have some spare servers that are not busy. And then an arriving job can be served by those spare servers. So then an arriving job always almost never needs to wait in the queue. So that's why this condition guarantees zero queuing, the queuing probability that converges to zero. Okay, so now I just want to briefly mention that, our proof approach. We have tried to establish the approaches in the literature that have led to very interesting results, a lot of results, but neither of them directly worked for our problem. So the first one is to bound the tail probabilities of an Lyapunov function through the drift of the Lyapunov function. And the second one is to derive expectation bounds through by finding a function that solves the Stein's equation. And as I mentioned, neither of those two approaches worked. So what we ended up doing is also based on the drift of Lyapunov functions, but we proposed a new way to construct a Lyapunov function and a new way to interpret its drift. And by doing this, we can bound the tail probabilities that are needed for bounding the queuing probability. So for more details of our approach, please see our paper. Okay, so now let me conclude the talk. So we studied a model where we have multi-server jobs. Those are jobs that can occupy multiple servers at the same time. And we propose a new scaling regime, which captures the joint scaling behavior of the server needs and the load. So both of them scale when n grows. And then we studied the latency of jobs. We give an upper bound on the queuing probability. And this condition in the upper bound, this upper bound allows us to derive conditions for the queuing probability to converge to zero. So this problem is a very new problem, and this is a very new model. So many problems are open for multi-server jobs, and a lot of research needs to be done. So here I'm just listing a set of questions that are examples for future directions. So first, we have characterized the queuing probability, but what is the expected queuing time? Can that also go to zero in some scaling regimes? And next, we haven't compared the different scheduling algorithms, and we actually wanted to know which scheduling algorithm minimizes the queuing time. And on a more technical level, the multi-server jobs can make the Lyapunov functions have jumps that are of different scales. So how can we handle Lyapunov functions with both large and small jumps to derive tighter bounds? Okay, so this is the end of my talk. Thank you for listening. If you have a question, you can draw me an email. Thank you.